And now we can move on to our bivariate statistics. Now we're still in descriptives. We can't make inferences about the population, but we do want to get an understanding of the relationship between our dependent variable and our independent variables. And this would be through scatter plots as well as our correlation matrix. So before we get into that in Stata, I do want to briefly go over what type of information we get from our bivariate descriptives. So both the scatter plot and our correlation coefficient R tell us a lot about the relationship between two variables. Again, we can't make inferences or causal assumptions about the relationship, but we can begin to understand how they move together. So from a scatter plot, we can tell both direction and strength of a relationship. So let's say we have this hypothetical scatter plot, which is going to take me a while to make. So the direction of the relationship simply refers to how the two variables move together. A positive relationship would mean both variables are moving in the same direction at the same time. So if one variable increases, the other will also increase. And a negative relationship suggests an opposite relationship. As one variable increases, the other decreases. So this example would be considered a positive relationship. And if we draw a line to best fit these data, we can also get an understanding of the strength of the relationship. The strength of the relationship simply refers to how closely these points cluster around the line of best fit. The closer they are, the stronger the relationship, and the further away, the weaker the relationship. Because of variability in our data set, we're probably never going to have a perfectly strong relationship with points crossing the line, with all of our points crossing the line. Right, now we can also determine strength from the Pearson R coefficient, our correlation coefficient. The correlation coefficient ranges from -1 to +1, with values of 0 suggesting no relationship at all, and further away from 0 would be a stronger relationship. Right? And positive values would be a positive relationship, and negative values would mean a negative relationship. And with the correlation coefficient, we can really only determine strength and direction, but we can tell a lot more from the scatter plot as well. And one important aspect of a scatter plot is whether the relationship is linear or not. And linear simply means that a line best fits the data, or rather that a straight line best fits the data. If a curved line fits the data, then this would be not linear. So an example of that might look something closer to this. If we remove some of these points and then add a couple more. So this might be closer to a curvilinear relationship. This would be not linear, where a curved line fits the data best. Right, and next we can determine if it's monotonic or not. And monotonic just means that it's always going in the same direction. It doesn't matter the slope of the line, just as long as the line is always consistently moving in the same direction. So a linear relationship will always be monotonic, but if it's monotonic, it doesn't necessarily mean that it's going to be linear. So for example, this curvilinear relationship here would still be considered monotonic. So even though the strength or the strength changes, the direction is always consistently positive. An example of this type of relationship might be hours spent studying stats and your understanding of statistics. So when you first begin, you might not really have a grasp of the terminology. It might be really jargony and confusing. But as you start to understand that, the concepts become much more clear. So in the beginning, you're all confused, and then you might have an aha moment where your understanding increases at a much higher rate. Right, the next thing to look for are outliers. And these are data points that appear not to fit with the rest of the relationship. So for example, you can have an outlier over here. And understanding your outliers is really important because it could actually change the line of best fit or the regression line. So for example, that data point would probably push the line of best fit to be much less steep, right? And then the final feature of a scatter plot to assess are potential gaps. And gaps simply mean that the data points tend to cluster in specific parts of the graph. So we might have this cluster of data points that don't actually have a relationship. And then this clustering up here also doesn't seem to have a relationship in isolation, but together it does appear that there might be some sort of relationship going on between your two variables. Now, just like with our univariate statistics, if there's something weird going on, if you have one outlier or it looks like it potentially be a curvilinear relationship, that doesn't mean you can't move forward with your regression. It's just something to keep in mind. It might contextualize your results a little bit better. Okay, so let's go ahead and do the assess our bivariates with our actual data set. Okay, and let's first get our scatter plots. The command here is two-way scatter. And we're going to do a scatter plot for our dependent variable ratings on all three of our independent variables. And a little hint here, whatever variable you label first after two-way scatter, that will go on the y-axis, and your next variable will go on the x-axis. It's generally best practice to put your dependent variable on the y-axis and your independent variable on the x-axis. Right? And then we're also telling Stata to print the line of best fit for these two variables. Now it's important to note that the line of best fit will always be a straight line. So even if a curved line best fit the data, Stata is always going to put a straight line. All right, so let's take a look at the scatter plot for ratings and hours spent researching. All right, so first thing to look for is direction. We can see that as hours spent researching the topic increased, so did overall judges' score. So that would suggest a positive relationship. We can also see that our data points do cluster relatively closely to the line of best fit, so that would probably be a moderate relationship. And there doesn't appear to be any outliers or systemic gaps. Right, let's take a look at one more scatter plot here. Let's look at the scatter plot for ratings and how innovative the project was. Again, as innovation increases, our judges' scores increase. There doesn't appear to be any extreme outliers. This dot up here might be influencing the line of best fit, but it's probably not too bad. This person clearly had a very innovative project and also a very high judge score. This also appears to be a moderate relationship as the data points do cluster fairly closely to the line of best fit, and no gaps, no concerning gaps or clustering. Right, the next bivariate descriptive we need to look at is the correlation coefficient. And we can assess the relationship between our dependent variable and all three IVs at the same time with the command pwcore. This is telling Stata do a pairwise correlation. Right, and because we're including all of our variables, our DV ratings, and our three independent variables, we're actually going to get what's called a correlation matrix with the relationship between all of our variables. So if we want to know how hours spent researching influences hours spent building, we'll also get that information. Now, when you include the comma sig at the end, you're telling Stata to also print the significance level or the p-value. And obs is telling Stata to print the number of observations. If you didn't include that, you would just get your correlation coefficient and you wouldn't be able to tell if it's a significant correlation or not. Okay, we can run that command and take a look at the output. We have this nice, neat table here. with this column showing us the relationship between our DV ratings and our three independent variables. So we can see that all three of these relationships are positive. A coefficient of 0.52 for ratings and hours spent researching would be considered moderate. A coefficient of 0.36 for hours spent building would be mild. It would be a mild relationship. And 0.66 for innovative would also be moderate, perhaps moderate to strong. Now, while there does appear to be a positive relationship for all three variables, only two of them are significant. So the first line for each relationship is the correlation. The second line is the significance level. So we can see that both research and innovative are statistically significant, while the relationship between ratings and bill and hours spent building is non-significant because the p-value is greater than 0.05. Right? And we can also see that there's a significant relationship between hours spent researching and hours spent building. This isn't quite as important since we're doing simple linear regression, but this will become really important when we talk about multiple regression. But this does make sense. The number of hours that people spend researching will probably correlate with the number of hours that people spend building. All right, so now that we've assessed our bivariate descriptives, we can finally move on to fitting our regression models.